Numbers are the foundation of mathematics. We use them to count, measure, and quantify the world around us. Real numbers are a vast and fascinating set of numbers that encompass all the numbers we encounter in our daily lives and beyond. Imagine a line that stretches infinitely in both directions. This is the number line. Every point on this line represents a unique real number. 0 marks the center of the number line. Positive numbers lie to the right of 0, negative numbers lie to the left. The number line is a powerful tool for visualizing and understanding real numbers. It helps us grasp concepts like order and magnitude. We can see that 5 is greater than 2 because it lies to the right of 2 on the number line. Real numbers are essential for everything from basic arithmetic to advanced calculus and beyond. They are the building blocks of mathematics. Euclid, an ancient Greek mathematician, gave us a powerful tool for working with integers: Euclid's division lemma. This lemma states that for any two positive integers a and b, there exist unique integers q and r, such that a equals bq plus r, where 0 is less than or equal to r and r is less than b. In simpler terms, this means that when you divide a by b, you get a quotient q and a remainder r. The remainder r is always less than the divisor b. Let's take an example. 17 divided by 5. Here a is 17 and b is 5. We can write 17 as 5 times 3 plus 2. So the quotient q is 3 and the remainder r is 2. Euclid's division lemma helps us understand the relationship between dividends, divisors, quotients, and remainders. It is a fundamental concept in number theory. Euclid's division algorithm builds upon the division lemma to find the highest common factor, or HCF, of two positive integers. The HCF is the largest number that divides both integers completely. The algorithm involves repeated applications of the division lemma. Let's find the HCF of 56 and 72. First, divide the larger number, 72, by the smaller number, 56. 72 equals 56 times 1 plus 16. Now consider the divisor, 56, and the remainder, 16. 56 equals 16 times 3 plus 8. Repeat the process with 16 and 8. 16 equals 8 times 2 plus 0. Since we get a remainder of 0, the algorithm stops. The HCF is the last non-zero remainder, which is 8 in this case. Therefore, the HCF of 56 and 72 is 8. This algorithm is an efficient way to determine the HCF of two numbers. The fundamental theorem of arithmetic is a cornerstone of number theory. It states that every integer greater than 1 can be expressed as a unique product of prime numbers. This factorization is unique up to the order of the prime factors. A prime number is a whole number greater than one that has only two divisors, 1 and itself. For example, 2, 3, 5, 7, 11, and 13 are prime numbers. Let's take the number 24 as an example. We can factorize it as 2 times 2 times 2 times 3, which can be written as 2 cubed times 3. This is the prime factorization of 24. The fundamental theorem of arithmetic guarantees that no other combination of prime numbers will multiply to give us 24. This theorem highlights the importance of prime numbers as the building blocks of all integers. Section 5. Rational and irrational numbers. We can categorize real numbers into two main types: rational and irrational numbers. Rational numbers can be expressed as a fraction where the numerator and denominator are both integers, and the denominator is not 0. Examples of rational numbers include 1/2, -3/4, 5, which can be written as 5 over 1, and 0.25, which is equivalent to 1/4. Irrational numbers, on the other hand, cannot be expressed as a fraction of two integers. Their decimal representations are non-terminating and non-repeating. One of the most famous irrational numbers is pi, which is approximately 3.14159 and continues infinitely without repeating. Another well-known irrational number is the square root of 2. The discovery of irrational numbers was a significant breakthrough in ancient mathematics, challenging the existing understanding of numbers and their relationships. Section 6. Decimal expansions. Decimal expansions provide a way to represent real numbers. Rational numbers have decimal expansions that either terminate or repeat. Terminating decimals. These decimals have a finite number of digits after the decimal point, such as 0.5 or 3.75. Repeating decimals. These decimals have a block of digits that repeats infinitely, such as 0.333, which repeats 3, or 1.272727, which repeats 27. Irrational numbers, as we've seen, have decimal expansions that neither terminate nor repeat. Their decimal representations go on forever without a predictable pattern. For example, the decimal expansion of the square root of 2 is 1.41421356. This sequence of digits continues infinitely without repeating, distinguishing it as an irrational number. Decimal expansions are useful for approximating real numbers and performing calculations. However, it's important to remember that decimal representations of irrational numbers are always approximations, since their decimal expansions are infinite. Section 7. HCF and LCM relationship. The highest common factor, or HCF, and the least common multiple, or LCM, are two important concepts related to the factors and multiples of numbers. The HCF of two numbers is the largest number that divides both numbers completely. The LCM of two numbers is the smallest number that is a multiple of both numbers. The HCF and LCM are connected by a fundamental relationship. For any two positive integers a and b, HCF of a and b times LCM of a and b equals a times b. Let's verify this relationship with an example. Take the numbers 12 and 18. HCF of 12 and 18 is 6, the largest number that divides both 12 and 18. LCM of 12 and 18 is 36, the smallest number that is a multiple of both 12 and 18. Now let's check if the relationship holds. 6 times 36 equals 216. 12 times 18 equals 216. As we can see, the product of the HCF and LCM is indeed equal to the product of the original numbers. This relationship is a useful tool for solving problems involving factors and multiples. Section 8. Real-world applications of real numbers. Real numbers are not merely abstract mathematical concepts. They have countless practical applications in various fields. Science and engineering. Real numbers are essential for measurements, calculations, and modeling in physics, chemistry, engineering, and computer science. From designing bridges to developing new technologies, real numbers are the backbone of scientific progress. Finance and economics. Real numbers are used extensively in financial transactions, stock markets, interest rates, economic modeling, and analyzing data trends. Understanding real numbers is crucial for making informed financial decisions. Cryptography, real numbers, particularly prime numbers, play a vital role in modern cryptography, ensuring secure communication and data protection in our increasingly digital world. Computer algorithms. Many algorithms and data structures in computer science rely on real numbers for calculations, sorting, searching, and optimization, enabling efficient software and applications. These are just a few examples of how real numbers permeate our technological world. From the smallest devices to global systems, real numbers are the language of science, technology, and our understanding of the universe. Section 9. Proving the irrationality of the square root of 2. The proof that the square root of 2 is irrational is a classic example of proof by contradiction in mathematics. We start by assuming the opposite of what we want to prove, and then show that this assumption leads to a contradiction. Assumption. Let's assume that the square root of 2 is rational. This means we can express it as a fraction a over b, where a and b are integers, and b is not 0. We also assume that this fraction is in its simplest form, meaning a and b have no common factors other than 1. Squaring both sides. If the square root of 2 equals a over b, then squaring both sides gives us 2 equals a squared over b squared. Rearranging. Multiplying both sides by b squared gives us 2b squared equals a squared. This means that a squared is an even number, since it's equal to 2 times another integer. Even square implies even number. If a squared is even, then a itself must also be even. This is because the square of an odd number is always odd, and the square of an even number is always even. A is even. Since a is even, we can write it as 2k, where k is another integer. Substitution. Substituting 2k for a in the equation 2b squared equals a squared, we get 2b squared equals 4k squared, which simplifies to 2b squared equals 4k squared. Dividing by 2, dividing both sides by 2 gives us b squared equals 2k squared. This means that b squared is also an even number. B is even, similar to step 4, if b squared is even, then b itself must also be even. Contradiction. We have now established that both a and b are even numbers. This contradicts our initial assumption that the fraction a over b was in its simplest form, with no common factors other than 1. Since our assumption leads to a contradiction, it must be false. Conclusion. Therefore, our initial assumption that the square root of 2 is rational must be false. Therefore, the square root of 2 is irrational. This proof demonstrates the power of logical reasoning and mathematical rigor in establishing mathematical truths. It highlights the existence of numbers that cannot be represented as simple fractions, expanding our understanding of the number system.